An ammeter is used to measure electric current. It's connected in series with the circuit so the current flows through it. The ammeter has a low resistance, so it doesn't significantly affect the current flow. When a wire is wrapped around the jaws of an ammeter multiple times, like 4 times in the question, it does not affect the current reading. Wrapping the wire increases the number of turns in the magnetic field, which will increase the strength of the magnetic field, but it does not affect the actual current flow. The ammeter will still display the same current, which in the scenario presented is 4 amps. An ammeter measures current. Current is the rate of flow of electric charge, typically measured in amps. 1 amp is defined as 1 coulomb of charge passing a given point per second. Think of current like the amount of water flowing through a pipe. The ammeter is designed to measure this flow. Ammeters are connected in series. To measure the current flowing through a circuit component, the ammeter must be placed in series with that component. This means the current flows through the ammeter, unlike a voltmeter, which is connected in parallel. Ammeters have low resistance. Ideally, an ammeter should have 0 resistance. This is because any resistance in the ammeter will impede the current flow and affect the reading. Real ammeters have a very low resistance, minimizing this effect. Clamping ammeters use electromagnetic induction. Many modern ammeters, especially those used for measuring high currents, use a clamp-on design. These clamp-on ammeters, also known as clamp meters, don't require breaking the circuit to measure the current. Instead, they use a current transformer to measure the magnetic field produced by the current-carrying conductor. The magnetic field is proportional to the current. The clamp meter works on the principle of electromagnetic induction. When current flows through a conductor, it generates a magnetic field around the conductor. The strength of this magnetic field is directly proportional to the magnitude of the current. The clamp meter has a magnetic core that surrounds the conductor. This core concentrates the magnetic field. A secondary winding within the clamp meter is used to measure the magnetic field. The changing magnetic field induces a current in the secondary winding. This induced current is proportional to the original current in the conductor. The meter then converts this induced current into a reading of the actual current in the conductor. Wrapping the wire creates a stronger magnetic field. Wrapping the wire around the jaws of the ammeter multiple times effectively increases the number of turns carrying the current within the ammeter's magnetic core. This can be thought of as similar to increasing the number of turns in the primary winding of a transformer. The magnetic field strength is directly proportional to the number of turns. So, wrapping the wire increases the overall magnetic flux linking the secondary winding. The ammeter reading depends on the induced current. The ammeter reading is ultimately determined by the current induced in the secondary winding of the current transformer. While wrapping the wire increases the magnetic field strength, the ammeter is calibrated to account for the number of turns in the primary winding. The ammeter's internal circuitry is designed to divide the measured magnetic field strength by the effective number of turns to derive the actual current in the conductor. Because the ammeter is calibrated to account for a single pass of the wire, the increased magnetic field strength due to wrapping is mathematically divided out, resulting in the correct current reading. The key is calibration. The ammeter is calibrated to provide an accurate reading based on the magnetic field it senses. Wrapping the wire artificially increases the magnetic field, but the meter's internal circuitry is not designed to interpret this increased field as a higher current. It interprets it as the same current flowing through multiple turns, which it then compensates for. Consider a simple analogy. Imagine using a lever to lift a weight. The amount of force you need to apply depends on the length of the lever arm. If you increase the length of the lever arm, you can lift the same weight with less force. The ammeter is like the lever, and the current is like the weight. Wrapping the wire is like increasing the length of the lever arm. It makes it easier for the ammeter to sense the current, but it doesn't actually change the amount of current flowing. The ammeter is designed to measure the current flow regardless of the strength of the magnetic field. Another way to think about it is to consider the ammeter as a device that measures the density of electrons flowing through the wire. Wrapping the wire doesn't change the number of electrons flowing through the wire, so it doesn't change the current. The ammeter simply measures the flow. If the ammeter reading changed when you wrapped the wire, it would be inaccurate. The ammeter is designed to provide an accurate reading of the current flowing through the wire, regardless of how the wire is configured. In summary, wrapping the wire around the jaws of an ammeter multiple times does increase the magnetic field strength, but the ammeter is designed to compensate for this effect. The ammeter is calibrated to provide an accurate reading of the current flowing through the wire, regardless of how the wire is configured. Therefore, the ammeter reading will remain the same, displaying the actual current flowing through the wire, which is 4 amps. Let's delve deeper into the underlying principles and practical considerations surrounding ammeter measurements, specifically focusing on clamp-on ammeters and the effect of wrapping a conductor around the jaws. The foundational concept at play here is Ampere's law. Ampere's law states that the magnetic field intensity around a closed loop is proportional to the electric current passing through the loop. Mathematically, this is expressed as the closed integral of B.dl equals mu0 times I, where B is the magnetic field, dl is an infinitesimal length element along the loop, mu0 is the permeability of free space, and I is the current. In the context of a clamp-on ammeter, the jaws of the ammeter form the closed loop. When a current-carrying conductor passes through the jaws, a magnetic field is generated around the conductor. The strength of this magnetic field is directly proportional to the current flowing through the conductor, as dictated by Ampere's law. The ammeter's internal circuitry then measures the magnetic field and converts it into a reading of the current. Now, let's consider what happens when the conductor is wrapped around the jaws multiple times. Each time the conductor passes through the jaws, it contributes to the overall magnetic field within the loop. If the conductor is wrapped 4 times, the magnetic field strength is effectively quadrupled, assuming each loop is tightly packed and contributes equally to the magnetic flux. However, the ammeter is designed to measure the current, not the magnetic field directly. It is calibrated to account for the relationship between the magnetic field and the current, assuming a single pass of the conductor through the jaws. The ammeter's internal circuitry effectively divides the measured magnetic field strength by the number of turns to derive the actual current. Therefore, even though the magnetic field strength is increased by wrapping the conductor, the ammeter correctly interprets this as the same current flowing through multiple turns and compensates accordingly. To illustrate this further, consider the equivalent circuit of a clamp-on ammeter. The clamp-on ammeter can be modeled as a current transformer. The conductor passing through the jaws acts as the primary winding, and the ammeter's internal circuitry acts as the secondary winding. The turns ratio of the transformer is determined by the number of times the conductor passes through the jaws. If the conductor passes through the jaws once, the turns ratio is 11. If the conductor passes through the jaws 4 times, the turns ratio is 41. The current in the secondary winding is inversely proportional to the turns ratio. Therefore, even though the magnetic field is increased by a factor of 4, the current in the secondary winding is reduced by a factor of 4, resulting in the same reading on the ammeter. In practice, there are some limitations and considerations to keep in mind. Firstly, the accuracy of the ammeter may be affected if the loops are not tightly packed or if there is significant spacing between the loops. This can lead to variations in the magnetic field strength and affect the accuracy of the reading. Secondly, the ammeter may have a limited range of current measurements. If the current is too low, the magnetic field may be too weak to be accurately measured. If the current is too high, the ammeter may saturate and provide an inaccurate reading. Thirdly, the ammeter may be sensitive to external magnetic fields. If there are other current-carrying conductors nearby, their magnetic fields can interfere with the ammeter's reading. In summary, wrapping a conductor around the jaws of a clamp-on ammeter multiple times increases the magnetic field strength, but the ammeter is designed to compensate for this effect. The ammeter is calibrated to provide an accurate reading of the current flowing through the conductor, regardless of how the conductor is configured. Therefore, the ammeter reading will remain the same, displaying the actual current flowing through the conductor. In a specific scenario described, where a circuit is pulling 4 amps and the wire is wrapped around the jaws of an ammeter 4 times, the ammeter will still read 4 amps. The wrapping of the wire does not change the actual current flowing in the circuit. The ammeter correctly measures the existing current, regardless of the manipulation of the magnetic field through wrapping the wire. It is important to use the ammeter correctly, including selecting the proper range and ensuring that the jaws are fully closed around the conductor. If there are any doubts about the accuracy of the reading, it is recommended to consult the ammeter's manual or seek guidance from a qualified electrician. The principle behind the ammeter reading remaining constant despite wrapping the wire can also be understood from the perspective of circuit laws. The fundamental principle governing electric circuits is Kirchhoff's current law, also known as the junction rule. This law states that the total current entering a junction or node in a circuit must equal the total current leaving the junction. In other words, current is conserved at any point in a circuit. When a wire is wrapped around the jaws of an ammeter, no additional current is introduced into the circuit. The current remains the same, regardless of the wrapping. The ammeter simply measures the existing current, and the wrapping does not alter the amount of current flowing. Another important concept is Ohm's law, which relates voltage, current, and resistance in a circuit. Ohm's law states that voltage equals current times resistance, or volts equals amps times ohms. Wrapping the wire around the ammeter does not change the voltage or resistance of the circuit. Therefore, according to Ohm's law, the current must also remain the same. In the given scenario, the circuit is pulling 4 amps. This means that the voltage and resistance in the circuit are such that the current is 4 amps. Wrapping the wire does not change these parameters, so the current remains 4 amps, and the ammeter accurately reflects this value. Furthermore, it is essential to differentiate between measuring current with a clamp-on ammeter and a traditional inline ammeter. While the principles are similar, the methods and effects differ. A clamp-on ammeter uses electromagnetic induction, as previously explained. It measures the magnetic field produced by the current-carrying conductor without directly contacting the conductor. This is why wrapping the wire does not change the reading, as the ammeter is calibrated to compensate for the increased magnetic field. On the other hand, a traditional inline ammeter is connected directly in series with the circuit. The current flows through the ammeter, and the ammeter measures the voltage drop across a known resistance. The voltage drop is proportional to the current, so the ammeter can accurately measure the current. Wrapping the wire around a traditional inline ammeter would not have the same effect as with a clamp-on ammeter. The current would still flow through the ammeter, but the wrapping might create a short circuit or other undesirable effect. In conclusion, understanding the principles of electromagnetism, circuit laws, and ammeter operation is crucial for accurate electrical measurements. Wrapping the wire around the jaws of a clamp-on ammeter does not change the current reading. The ammeter is calibrated to compensate for the increased magnetic field and accurately reflect the actual current flowing in the circuit. It is important to always follow proper safety precautions and use the correct tools for electrical measurements. If there are any doubts or uncertainties, it is best to consult a qualified electrician. In addition to the theoretical understanding, it is beneficial to consider real-world scenarios and practical applications. For example, electricians often use clamp-on ammeters to measure the current flowing in large cables or busbars. These cables and busbars are often difficult or impossible to disconnect, so a clamp-on ammeter provides a convenient and safe way to measure the current. In industrial settings, clamp-on ammeters are used for troubleshooting electrical systems, monitoring equipment performance, and ensuring compliance with safety regulations. For example, an electrician might use a clamp-on ammeter to check the current draw of a motor to determine if it is overloaded or malfunctioning. Similarly, a clamp-on ammeter can be used to measure the current flowing in a circuit to verify that it is within safe operating limits. In residential settings, clamp-on ammeters can be used for a variety of purposes, such as measuring the current draw of appliances, identifying overloaded circuits, and troubleshooting electrical problems. For example, a homeowner might use a clamp-on ammeter to check the current draw of an air conditioner to see if it is running efficiently. Similarly, a clamp-on ammeter can be used to identify a circuit breaker that is tripping frequently due to an overloaded circuit. Furthermore, it is important to note that clamp-on ammeters are available in a variety of types and models, each with its own features and capabilities. Some clamp-on ammeters are designed for measuring alternating current, also known as AC, while others are designed for measuring direct current, also known as DC. Some clamp-on ammeters have additional features, such as the ability to measure voltage, resistance, and frequency. When selecting a clamp-on ammeter, it is important to choose a model that is appropriate for the intended application. It is also important to read the ammeter's manual carefully to understand its features and limitations. In summary, clamp-on ammeters are versatile tools that can be used for a wide range of electrical measurements. They are based on the principles of electromagnetism and circuit laws, and they provide a convenient and safe way to measure current without disconnecting the circuit. Wrapping the wire around the jaws of a clamp-on ammeter does not change the current reading, as the ammeter is calibrated to compensate for the increased magnetic field. When using a clamp-on ammeter, it is important to follow proper safety precautions and select a model that is appropriate for the intended application.